please sit down, and Professor James Barber to the podium immediately. No, I'm presenting you. Okay. Do you remember that you dubbed me to something the other day?
Yes.
That's good. Sit down. I don't think I have to present the next speaker. He is known for everyone, I think. And I will just tell what he is going to speak about. Hydrogen derived from water as a sustainable solar fuel. Learning from biology.
Yes, that was my title of my talk, which I've left in London. And so I don't have a title anymore. And I've had to make up this talk here, but I hope I think it's okay. Now, this is the gentleman that we're really honouring this afternoon, the whole meeting, but particularly this afternoon. Actually, he was quite good looking. The only thing is, he did tend to want to follow me, whatever I did. If I wore a blue shirt and light trousers, he wore blue shirt and light trousers. It didn't matter what I did, he did it. And the only thing was, he was watching my publication list all the time, and he'd say, "Oh, Bob, I've got to get up to him." He's so competitive. Anyway, Bert's research, of course, has been in the areas of photosynthesis, biological membranes, protein membrane purification, light stress in plants. You've heard a little bit about that today. And he's authored, I think, over 300 papers, about 300 publications, all refereed, I hope. And he probably put in a few that weren't. Remarkably, he produced 32 of them after he became rector at Linköping University. He was such an unusual rector of a university because he ran a research group and published lots of papers, and that was just so impressive. And also we did a book together. And that's when he became rector, during the time when he was rector of Linköping University. I'm afraid his research output fell off when he became CEO of ESF, right? He no longer had a lab, but as a rector, do you ever know a rector of your universities who had maintained a research lab, or established one in his case? Very good. Now I've got to find out how to do this. Do I press that one? Or do I press that one? No, that one. Yes. Now, it all started, actually, his research career, my interaction with Bertel, way back about 1978. And we met up about at that time. And this is his thesis, separation of spinach, chloroplasts, and lamellary fragments by phase partitioning. And he was very influenced, of course, by his supervisor, Albertson, who had been developing the two-phase system, yeah. And the thesis was very important, but he was very shy. No, it's impossible he could be shy. He was shy about his results because they were controversial. And the main result really was, let me go on the next one, was that he claimed that by using partitioning, phase partitioning, that he could separate out the grana membranes from the, if you like, the non-granule membranes of higher plant chloroplasts. And not only that the ones that he took, that he obtained from the grana were inside out. That is, they were producing oxygen on the outer surface rather than on the inner surface. Well, this was a totally new type of preparation. Nobody had made inside-out thylakoids or grana membranes. But as somebody said, it's been said several times in the meeting, this turned out that this preparation, which we call B3, what turned out to be entirely, more or less entirely, photosystem 2. And somebody said that they went to Stockholm to see this photosystem 2 preparation. Now, of course, it was a piece of membrane, but it was, Bertel exploited it, of course, as being a very pure form of photosystem 2. And I might say a lot of the work that was done on sodium potassium ATPases, for example, was done on membrane fragments. So there's nothing wrong with using membrane fragments. But it led to a model, a very important model, that there was a separation, therefore, of the PS1 and PS2 between those different regions, between the partition region of the stacked membranes was all essentially, at that time, he didn't like to say it was all photosystem 2. He put a few photosystem 1s in. And you can find the same diagram by Barber in 1980, drawn by my wife Lynn, who is here? No, is she here? She's here. We used, it wasn't quite, well, it was about, looked more or less identical to that. And, but he had published it first in his thesis. So he's the discoverer of lateral separation model. And this was a very hard concept to get over to people because they thought at that time that the two photosystems must be together, you know, the energy transfer between them and so on and so forth. So it was a very hard concept to get over. And I was also coming along with the same concept. And that, I've got to say, that's why we're good friends. Is it not? We could have been very competitive. But on the other hand, we were in the same boat together with this the separation of the photosystems, and nobody seemed to understand it, you know, it was too revolutionary at the time. But Bertel did a very wise thing. He went off to Australia, and there was the dream team. There was the two Andersons, Bertel Anderson as the young postdoc on his EMBO fellowship, which should have only been used in Europe, somehow used in Australia, and Jan Anderson, who had been a major player in bringing the idea of photosynthetic processes into a membrane, into what was called the Singer-Nicholson model of the membrane, that proteins were actually in the membrane. I know it sounds ridiculous now, but the proteins were in the membrane with lipids around, you know. And she actually was the first, in a wonderful, wonderful review she wrote in BBA while she was on sabbatical in Cambridge, that brought together membrane biology and photosynthetic electron transport and light harvesting. And Bertel, therefore, instead of coming to London to be with me, he went off to Australia because I had similar ideas. And in Australia, he was at the CSIRO, and there they had a good graphic people. And so the idea of this lateral separation that he persuaded Jan that it was true after doing some biochemistry there. And this was drawn like that, beautiful drawing. You see, with the PS2 in the partition regions where you've got close membrane interaction. Well, on the surface of the grana or on the non-granal membranes, you have both photosystem 1 mainly and the coupling factor of John's ATP synthase. This was the model that he published in 1980, just about the time, just after I published mine, actually. And the story goes, I think Bertel went on holiday in New Zealand, and he came across this Feb's letter paper that had just come out, and it was by me, just me, and I had somewhat of a similar model based on a completely different background. But he said, bloody hell, this, and he phoned up Jan. He said, there's this Barber bloke, he's coming up with something similar to us. We've got to get our paper out and make certain the diagram's better than his. Anyway, that's how it started, and this was Bertel's great contribution, actually, to... oh, can I use this to go forward? Yeah, good. And so that went into the textbooks, and it was the beginning of Bertel's career, and it was quite a big bang. And he also, like me, had the same trouble trying to convince people of it. People said it was a load of rubbish and so on, but he was right. Now, those little drawings in there, we just used circles off a lecture set, but you see they're very fancy drawings there, of PS1 and PS2, are actually protein complexes, of course. So the next step was these blobs. What are these blobs exactly? And from then on, many people, of course, contributed to understanding what those blobs were. And those blobs are shown here as photosystem 2, photosystem 1, the ATP synthase, and the redox coupling complex here, the B6F complex. And over the years since that time, we built up these pictures. Now, Bertel concentrated on photosystem 2, and other people were doing this. So did I. So we both followed the same track. We were then very good friends about finding out what was the nature of the blobs. Many other people too. And there were two approaches. There was the standard biochemistry approach, that is, isolate the complex, run JAWs, and try to do N-terminal sequencing of the various proteins that came up, which were more than 20 for that complex. And of course, at the same time, the genes were starting to be discovered, antibodies were being made, and the whole thing was being mapped out. So this is Bertel's contribution to the blobs. He actually contributed greatly. He was the first really to run very good JAWs. I've forgotten the PhD student's name now, but they ran very good JAWs to show up these low molecular weights, all about 10 kilodaltons, around that 10, 9 kilodaltons, and identified some of these proteins. He also was able to look more closely at the proteins that make up the so-called LHC complex, and discovered that some of them were phosphorylated, and some of them were dynamic and actually moved in and out of the PS2. Something we won't have time to talk about now. More subunits there he worked on. And particularly also on the extrinsic proteins, which cover the catalytic center, the manganese catalytic center. And he isolated those, particularly the O protein, and characterized them. And of course, as you heard in the last two talks, really, but particularly the last talk, and from Peter Nixon, he started to get very interested in the turnover of the D1 protein and the effect of stress on that turnover and repair system of photosystem 2. I don't talk much about the repair system of photosystem 2 these days, but is a part of the oxygen evolving system, that this enzyme repairs itself because you're dealing with hot chemistry and you're producing radicals, particularly singlet oxygen we talked about, and it can't protect itself in the same way as other reaction centers against singlet oxygen, which I could explain if anybody wanted to know. But these are the things that Bertel did. Fantastic work, and it's hard to believe he's done that. Now he moved on ultimately into administration, really. But of course he's been very successful at. Now, one of the things that Bertel, about the last bit of work he was doing in Linköping, was showing that there was a GTP activity associated with D1 turnover. And nobody's mentioned that before here today, but which seemed to involve the PSPO protein. And two excellent papers, well, 3 papers were published on that at that time. And you were very excited about that, if I remember rightly. Even that you were rector and busy trying to run a university at the same time. And about that time, actually I did a little mini sabbatical with Bertel in Linköping. And of course, by then we had already got the structure of the PSPO protein, by the way, which was a very difficult protein to get the structure of. But here it was, and here in a paper that we're with Bertel, we modeled the where possibly the binding site was for the nucleotide. And that work has really stopped now, actually, Bertel. It's not really being followed up by anybody. I don't think so. By the way, this was our structure of higher plant PS2 at that time, put on the front cover of BBA for a whole year, actually. Okay, so that's was all very good. And another thing that Bertel and I did together was we started to think about artificial photosynthesis. And we wrote an article, is this the Nature? We wrote a Nature article, actually, revealing the blueprint of photosynthesis. And I always remember Les reading it over. I never could get it to the quality I wanted to get it to, but I think you refereed it, actually, I don't know. And because we got something wrong and he picked it up, of course, as usual. We discussed the whole possibility of using the knowledge we were now extracting from photosynthetic organisms for artificial photosynthesis in order to exploit solar energy. And Starton and Moser were already thinking about this, and they had a model here of the way perhaps an artificial system would work with a donor and an acceptor side on here, a titanium oxide semiconductor surface, right? And it's a very, very nice picture, and we use that quite a lot. And the paper has been quite well quoted, I think. You know all the citations, maybe a few hundred or two.
Because it didn't work.
No, that was never in the paper. That was, no, we didn't have this in the paper. I've just put it on the slide. On the slide in recognition of your foresight of artificial photosynthesis. Well, also Bert was, of course, because we collaborated quite a lot, he was a regular visitor to Imperial College, and I often ran meetings there and so on. But there he is. Of course, he always mixed with the top people, you see. There is Lord Porter, Nobel Prize winner for flash photolysis, and of course, this chap here. And there's Lynn, who at the back, Lynn, you can see yourself. There's David Klug. There's a number of, where's James? James, where are you? There's Peter Nixon. James, oh, he went sick that day. I know what he said. He's not there. I don't understand that, but James was also a part of the whole group at Imperial. There's a guy called Roy Mansfield, who was an excellent PhD student, as was this chap here, by the way. So I had many photographs of Bertel in funny positions, often after he drunk too much. But this was one funny position. I think you see, we said, beware the bull. And we were out doing a country walk, and I took this photograph of him. And this is supposed to be horns, is it? Am I meant to be horns?
Yeah,
oh, yeah. And he's looking very tough. And he was getting ready at that time to become the president of NTU. So they didn't know what was coming. This was the man that was going to come here and take over the place, which he did. There were bulls there, actually. You were a bit scared to go a bit further into the field, weren't you, actually? Yeah. I don't blame you, actually. Okay, I'm going to switch now to a little bit of myself, of talking about things. Now, this is the 5 billion year clock, and we are now about 4.6 billion years round from the Big Bang there, and oh gosh, we haven't got long to go. Actually, the anticipation that the sun will become a dwarf, red dwarf or something, in about 10 billion years. So we can go all the way around again. But our little line for us is very short indeed. Now,
you have 10 more minutes.
Is that all I've got? Really? 10 minutes? Oh, that's okay. You are boss. I can't believe it. Oh, it was planned to be about 10 minutes before the end at this stage. The fact of the matter is, we had chemical evolution. The planet became cooled down. There was a mass of different compounds in the primeval sea, and we had these outcrops both underwater and on land from volcanoes and so on, and life started. But this wasn't simple life. Over those billion years there, this life is very complicated. Already we have ribosomes, we have ATP synthase, presumably. The cells, these anaerobic cells, were very complicated, and they were getting their food or their reducing equivalents to drive their chemistry from things like Fe2+, from ammonia perhaps, from sulfite, and many other reduced compounds that were available, organic acids, in that primeval sea. Then, amazingly, I think they got to to a stage where they were having an energy problem. There wasn't any longer enough energy to sustain what must have been quite a lot of life. A very simple life. Everything's prokaryotic. There's no multicellular organisms. And we came to a stage, and that just like we do at COP21 the other, we've got an energy problem. How are we going to solve our energy problem? Well, look, water is a source of hydrogen. That's it. Get the hydrogen or reducing equivalents, high energy electrons out of water. And the water splitting process appeared. Big bang of evolution, because once water was used as a source of electrons and protons, or particularly of electrons, you could then diversify, you could become multicellular, diversify in many different ways, and ultimately end up with whole organisms, then with ozone building up in the atmosphere. Life on land could start to evolve as well because of shielding against UV radiation. So there was an energy problem here. And at the moment, of course, with our own species, we're getting very cramped on planet Earth, and we're doing things that perhaps we shouldn't be doing, which may interfere with the natural Darwinian evolution. And we are now also, in a sense, at a crucial stage in terms of energy, but for a different reason, because the reason is the lack of the production of pollution, which could have serious effects. Okay, I'm going to whip on. Now, what we have to remember, that actually, as biology knew, planet Earth is energy rich. We have a lot of energy falling on our planet from the sun. In fact, the usual statement is 1 hour of sunlight is equal to all the energy consumption of the planet by humankind. In fact, I had an email from for Harry Gray this week. He said, well, it's not 1 hour anymore, 60 minutes, it's 80 minutes because we're using more energy. But this is a nuclear fusion reactor, and we have a lot of energy available to us. It's a question, how can we use it? Of course, we have technology to know how to use it. We've got photovoltaics. We know how to turn sunlight into electricity. We also have wind, which is also solar, because it's the thermal gradients of the planet that gives us a wind due to differential heating basically between the equator and the poles. So we have wind, solar. But we also have hydroelectric, which is, again, solar. The heat of the sun is brought about evaporation, and then the depositing of rain, and the use of that rain at higher elevations to drive turbines to make electricity. And wave power is also electricity. If you add up all the solar energy we're using at the moment by those different technologies, it's about 10% of our total use of energy at the moment, 10%. It's not bad. The rest of it is almost more or less fossil fuel. Over 80%, somebody put up 90% just now, but well over 80%, or nearly probably 90%, because we do have some nuclear, of course. Now, let's go back to growing the crystals of photosynthesis. While he was busy, well, you were just moving into administration, and I was there. Shall I go into administration or not? I actually did consider joining him, actually, at ESF. And no, I carried on. Well, we've got to get a structure of photosystem too. And we grew crystals, as you all know now. We got a structure. When you say a structure, this has 5,000 amino acids. We didn't only have to look at the manganese cluster, we were getting the structure of the PSBO protein, for example, in blue there. We were determining the nature of all these small subunits that Bert had identified on the SDS gels. All of them had to be modeled. Luckily enough, we had gene sequences in order to allow us to do the modeling. And if anybody wants to check this X-ray structure against the 1.9 X-ray structure, you'll be surprised how similar they are. It was a tour de force. I'm very proud. There was no mistake whatsoever. Of course, we had struggled a bit with the resolution of the manganese cluster. In the paper that finally came in 2004, I made a statement in the in the abstract. The data strongly suggests that the OEC contains a cubane-like manganese-3 calcium O4 cluster linked to a fourth manganese by a monomu oxo bridge. So that was one of the main conclusions. There were many main conclusions. The paper now, by the way, everybody seems to be telling how much they cite the paper, but I think it was about now, it's about 3,090. I'm trying to catch up with John, actually, with his paper. Okay, so that was the cubane model that we suggested. Some people were very critical of it. It was a completely new structure in science. There was nothing like it in the chemistry world, and there was nothing in the biochemistry world that had that structure. I must stop at this moment and recognize, how did we come up with this cubane? Well, we were looking at the density, and with myself and Sawata, I would say, yes, it looks as if it could take a cube. And I said, it is possible it could be cubane. It had been suggested by, Gary Bruvik and Crabtree. Are you here, Gary? You had suggested it as an iron sulfur Fe4S4 cube. So I said to, let's put in a Fe4S4 cube. And it looked pretty good. And that led us on then to the manganese 404 cube. And then because we got anomalous diffraction data, told us that it couldn't be that. We had to have a calcium in that cube, which was a surprise. And that led then to the model that actually Wolfgang showed this morning of the cube. And I'm very proud of this. This is in the science paper, because we identified the possible reaction site for water oxidation here between the manganese and the calcium. These X's were supposed to be sort of substrate waters. And the rest of it wasn't bad, we didn't have it all. We didn't have bidentite binding. We didn't do a perfect job, I got to say, but we did pretty good. We identified this residue of CP43, which was totally unknown. It was, and we could see a proton channel and so on. So it was pretty good, I must say. At that time, to me, and I wrote it in the science paper, but I also wrote another paper afterwards, the same year, Barber here, that the structure that we had proposed fitted very well to the proposals, and again, it was mentioned just now, of particularly of Vincent Pecorio, and he said, nucleophilic, he suggested that before the structure, that the OO bomb formation was a nuclear attack by a calcium-ligated hydroxide onto an electrophilic oxo group ligated to a highly valent manganese to achieve the critical OO bomb formation. I thought, wow, that's exactly fits this structure. Here we have this possibly a high valency manganese, and here we had a hydroxide binding to the calcium, and they're about 4 angstroms apart, perfect distance. So right from the beginning, I liked this mechanism. I realized there could also be oxyl radical mechanism as well, which would be energetically the same. So, and I presented this before the publication of the paper in the West Coast photosynthesis meeting in the USA in January 2004. One dark night. Rick Debus was there. Rick, do you remember? The joy of my life, of course, was when, particularly when, of course, the paper came out from the Japanese group, Shen and the others, where they also concluded that this cubane structure was essentially where they found the same structure, except they had this extra bond, the O4, and that was very satisfying. But even more satisfying was the work of, I'm sorry, I know it's not pronunciation right, but Zhang. Can I just call you Zhang? Of this man here, where he synthesized in 2015 this complex, which is also the same as this one. That is, it's a manganese 4 calcium O4. And quite frankly, you can take his coordinates determined at 1 angstrom resolution or better, and they almost fit. It fits more or less on top of our original structure, which was determined from low resolution information. and with a little bit of brain work, you know, about what distances to put and so on. So unbelievable I mean, in classical chemistry, of course, to prove something, you synthesize it. And of course, Sigburn, Pear, as he showed before, used DFT calculations before the high resolution structure I like to use the word refine our original structure in a remarkable way, where he brought in this extra oxygen bond, which we would never have seen. And that was, I don't know how he did it, but he did it. But not only did he do it, so did Holger. Where's Holger? Using quantum mechanical calculations again, they also concluded that there was an extra oxygen bond to the Dangular manganese. This one here, I suppose. It was just amazing. And again, this is 2008, before the confirmation of our original model. Of course, a lot of people were very negative about it, as always. And then came along, I already knew about carbon monoxide dehydrogenase, that it had a geometry very similar to the photosystem 2, except it was an iron-sulfur cluster, really, with a nickel rather than a calcium as the metal in the cubane, and with a dangular iron, exo-iron, as Holger would say. So here you can see that they're not exactly the same, but they're very similar. And Holger said this week, yesterday or whenever, these are unique. Where is Holger? You said they're absolutely unique. There is no other examples of this heterocubane structure with an external metal. And yeah, in nature, as far as you know. So there we are. We've got two enzymes with a similar geometry at a catalytic center. How am I doing? Should I stop?
5 more minutes.
Oh, that's more than enough. I'm nearly finished. But so I used to show you all structure as an example of a cubane type model, Holger. And of course, it was Robert Huber who told me about it many years ago. Because just as evidence that you could have such a type of structure. But of course, actually the enzymes in a way are quite similar in what they try to do, at least when they're going in the forward direction at 40,000 turnovers. This one uses the energy of, carbon monoxide dehydrogenase. It's using the energy of the oxidation of carbon monoxide to carbon dioxide to, Holger doesn't like me to say split water, but to remove protons and electrons from water. So it's an oxygen transfer reaction, actually. And in water, in photosystem 2, we have the same thing, really, in a way, is that we're going to have an oxygen transfer, oxygen atom transfer, and we're going to remove 4 electrons, 4 protons, which are then going to drive reductive chemistry in the cells. And this is the same. This is used also to drive reductive chemistry of the organisms that have this enzyme. Holger said yesterday it can also be used to just get, get rid of excess carbon monoxide, you argued, I think, didn't you? It was a way to get rid of excess carbon monoxide. Pardon?
Organisms use the electrons.
Yeah, they use it.
But no one often has hydrogen.
Yeah. So there's this anaerobic organism, possibly goes back before the oxygenic photosynthesis, using water as a source of reducing electrons to drive reductive chemistry in their cells. Now, just last minute, going back to this model. Now, I wanted this I believed in 2004 or 2003, and in a way, I still believe it, that we're dealing with a nucleophilic attack of an oriented OH on the calcium onto a highly electrophilic oxygen. That means it's got no, it's electron deficient. Why is it electron deficient? Because here you've got an oxidizing battery. We've got a positive charge we've mentioned before accumulated, and we've got this high valency, high oxidizing manganese cluster, all closely packed in here, drawing electrons away from this Dangular manganese and particularly from the oxygen. Now, Litching said yesterday that he believed they could even have a manganese 7. I don't think formally you could write a manganese 7 there, but you can see the effect of this drawing electrons away from this manganese 5 and making it even more oxidizing than manganese 5 itself. So you could almost, because you could almost call it a manganese 7 maybe, but of course the manganese 7 would be, electrons would have removed completely. But the electron cloud is pulled all the way over here towards the oxidizing battery and leaving this oxygen really very active for a nucleophilic attack. And so I've got to say, I find it hard to get away from this mechanism, although everybody here would tell me it's all nonsense. No, they shouldn't, actually. And here is the cycle. It's not very clear, I'm sorry, but here's the nucleophilic. It's a very simple model of losing protons and electrons during the state cycle, ultimately arriving at this high valency manganese and manganese 5 and the OH on the calcium and the nucleophilic attack. And I just published this in Nature Plants based on the comparison with carbon monoxide dehydrogenase. There is a question of ammonia. I also believe that ammonia is sort of affecting, if you like, a carousel mechanism. But the carousel mechanism is very simple in this case. This ammonia replaces the water here, the second water on here, and therefore blocks this water ever being a substrate water, and therefore slows down the cycle. That is, by having two water molecules on the manganese 4 on the calcium means that it's loaded, ready to maintain a rapid optimal rate of kinetics for the cycle. So there's the two water molecules are going to substrate water molecules on the first one. Then these can become available for the next cycle, and then the binding of the next water molecules can be done slowly and not limit the overall turnover rate. If you put ammonia on one of them, you're going to block that optimization and get a much slower rate of oxygen evolution. This is exactly what you see. With that, I don't know. I think that's it. I think that's it. It isn't quite. I think it's. I just want to say one more thing to that slide, in that I'm very passionate about taking the knowledge base that we're getting from photosynthesis to see if we can help in what is a major problem and agreed by 200 countries, more or less, of the world, which is unique to get them together, that we've got to bring down the CO2 levels that we're putting into the atmosphere at the moment. And in fact, the target is to have 0 CO2 emission by the end of the century and 80% by 2050. And I believe that our field has to contribute to that effort to bring up a new technology in which we can think. And I was going to show a little bit of that, but I'll finish.
Congratulate Jim to, I think, the most entertaining talk we have ever had.
Oh, I'll carry on.
You get a special...
My darling.